Hello and welcome to the 41st podcast of the Motor Doc Podcast. And this last week we had a lot of fun I did. If I had a whole crew, we would have had a booth there, but unfortunately we were at the Vibration Institute Annual Technical Conference. I didn't ask about the numbers there. It was extremely well attended. We sponsored the notebooks and lunches for the week. I was not able to get there for the pre-workshops because of some reports we had to get done from the prior week. That's the one where we found Sasquatch, but neither here nor there. And then I did a presentation on Thursday having to do, this is actually the slide from the presentation, evaluation of energy losses due to degradation. So this was the culmination of that work that we were doing, advancement, because we're not finished yet, of the work we were doing on relating vibration data to the energy losses in a machine, et cetera, et cetera, et cetera. So there was a lot of lessons learned in it, and as I had said, you had to be at the conference in order to see the presentation and the actual algorithms. But I'm going to use some of the data today to talk about what is the impact on how we do maintenance. Do we leave something, I did this alignment and I'm good enough, or I made this improvement in balancing and did enough. And we'll stick with balancing today, just because it's quicker and easier. But I'll show you the calculator we made. When I finished putting the presentation together and I was verifying the algorithms in the presentation, because although I tell everybody I don't like math, this one was definitely math heavy. I went ahead and took that, tossed it into ChatGPT, had it generate some code for me, turn that code into an executable and a quick calculator for the class. Now, I am going to make one eventually available when I have a few minutes to generate one that we will put on the website. So if you have vibration data, you can enter something in and you can see before and afters and do other experiments in order to see how precision maintenance or lack of maintenance has an impact. And that'll be based upon different stuff. I do want to show a couple of conclusions from the presentation, and those had to do with I'll do a version of it, not the advanced version, of course, in another podcast. But let's get down to some of the data. This has to do, so some of the presentation, like this one where it says 25 horsepower motor, this was the initial investigation where we said, okay, we're going to use kinetic energy calculations that are being used by some of the vibration transducer companies to either charge batteries in the transducers or to wake up the transducer in order to send a wireless signal, or send a signal, wireless or not. And we were looking at things such as, and I believe I've talked about this in an earlier one, the movement, stiffness and dampening effects that we were using motion amplification to help us with. And then, of course, we have the modified empath, and I have to get, I've told people it's now available, the ability to build in a vibration analyzer into the empath. And last week we got to use it for that, where we went and we took ESA on the machine, and then we did to different components of a gearbox so that we had data in addition. Really, I did it for the presentation, but in any case. So here we have, this is probably, let's go over here. So this is my horizontal vibration, 0.06 and so on. This is on one of the machines. And then this is the losses in kilowatts or watts. So if I want to do this in watts, that would be close to 120 watts versus 0.12 kilowatts. That's really the only difference there. And then again, something similar here, it looks a little bit lower, and that's because we took the data at a different time. That's important to understand because as I'm taking the data over time, there's going to be small variations. What that means for us, because most of what we're going to look at is in watts, and only on very large machines should we even see kilowatt defects. And I've shown some in the past on this podcast, and we'll show more. It's kind of a focus for me as KPI for the reliability and maintenance team to relate to energy and emissions goals for the company. So energy has a direct tie to the P&L, et cetera, et cetera. And just like my opening line at the conference, I agree. There is a correlation between a solid reliability program and safety. But I can't sell a reliability program to the C-suite by going in and saying, how many people did you murder last year? We're going to reduce that by half. It just doesn't come across very well. I'd rather go in and say, hey, we're going to have a significant impact on the cost of operating the business through energy, and we're going to help you meet your whatever your emissions goals are, just through the act of the maintenance program. And Department of Energy had put out a minimum of 14% reduction in energy, which relates to actually a slightly higher amount of emissions, right? What does it harm? It doesn't harm anybody. I tell everybody I'm climate agnostic. I don't have the information to say one way or another. But people believe it. My customers believe, in some cases, believe in it. So I'm going to present it with actual valid data based upon what I get from EPA and DOE. I've always had to present it that way. All the grants I requested, all the programs I had to do going back into the early 1990s and then later at the Energy Resources Center at the University of Illinois, I had to constantly, relate the work we were doing back to also greenhouse gas emissions, right? It's been a thing. So we're going to follow along with that. So there's some good news with that too, because I see a lot in the news, and to be perfectly blunt, what I'm watching over the years is the reduction in greenhouse gas emissions per gigawatt hour of energy, or megawatt hour of energy, I should say. So if I go in, and it used to be, 1.4, if you're doing a reduction, 1.4 metric tons of CO2 per megawatt hour of electric power. Then it became 0.909. Up until the beginning of this year, it was 0.709. And this year it's 0.699. That is a steady progression in what we're doing here in the States, and it is, let's just say the air is cleaner. I remember the 80s going to certain cities and just, because I have a very light case of asthma, and just having a hard time breathing. Now, it's not an issue. So, anyways, neither here nor there. I'll get down off of that soapbox. So if somebody asks me about that, I'm climate agnostic, I'm politically agnostic, I don't care. I do care what my customers care about. So when I go in and I say, okay, there's this much energy, we just had this happen last week. It's like, okay, you're losing this much energy through the machine. Was I then just talking to the technician? No. Plant manager swung by to have a discussion with me, because we also identified that this particular machine, it wasn't as urgent as it was being made to sound to rip all the equipment out and shut down half the plant. Turns out that the losses were extremely low. The condition appeared to be very stable. And I said, and if you're listening, Chad, borescope. Go in with borescope and take a look and verify. Always verify. We're using black box technologies with squiggly lines, sometimes video, to try to identify what's going on inside a box that we can't physically see inside the box. So you don't want to do that most of the time, but when you do see something triggered, there are other ways of doing verification. So, we do it in wind. When the cost is that astronomical and you're going to take an asset out, you go in afterwards and you go with a borescope and you verify the test results from vibration or ESA or whatever else. You want to make sure you don't have that, 5 or 10% of the time when you've got a false positive. But anyways, so the combination of stuff, right? So those are the values there. This one also had a slightly loose base. That one was vertical. This one's horizontal. The end result is my vertical readings are higher than my horizontal. My horizontal readings are higher than my vertical readings, as you can see here. Now, very low, and I did that deliberately. We selected very low readings so we could see what was going on. So here's the horizontal movement, and what are we going to do with that? Well, we're going to take a look at the remaining unbalance, because that's what we had introduced into the system. So here we're talking about, I think it's right around 20 watts. And then here's the thing here. So we knew we needed weight as part of that. So we needed to know the kilograms of the machine, the watts involved, and then what the vibration is. We did discover a few things, like it is true, the losses having to do with friction and the bearings, friction and windage, as long as the speed remains constant, those remain constant. So whether I'm looking at an unloaded or fully loaded machine, those losses that I calculate should remain the same. It also means in vibration, my peaks aren't going to change very much, and that's an observation we've had. And then this is just the kinetic energy, and which we're showing the pretty significant difference between the two. And in this case we're talking. Let's go back. We're talking, in pounds of CO2 versus metric tons of CO2. So, is that a big deal? Well, when we start talking about the other stuff, so I'm taking a single peak measurement on a good machine and saying, okay, these are low. I have gone into a few cases with larger machines and said, hey, here's the situation, yada, 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 and so on. So, we then applied it in a whole bunch of machines in the field. This is a compressor. There's the losses right around 400 watts and the vibration, but the weight was higher. So we did discover that there's a curve associated with it in order to come up with a relative value that also worked on smaller machines and a couple other things. So, we did the same thing, and I believe I probably have done this here. Buckingham Fountain, the motors associated with it. We looked again at low vibration values. The work we did last week on a ball mill. Here, just for fun, there you go, ball mill. That's the noise is basically big steel balls rolling around and they're grinding up ore. But we were looking at a condition in this gearbox here and did find that, because we're having to drive through it, we can read the energy loss for that in the air gap of the machine. So what the machine sees in losses inside that machine. I'm sorry, it's not absorbed by the coupling. I've heard that statement. Well, it goes right along with, I was sitting at the Vibration Institute conference, and somebody had told me that a salesman for a competing, not a machine learning based DSA system kept saying, with that system, with the empath system, you need a PhD, da 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 da. Well, I'm sorry that their system is that complicated that they need a PhD to understand what they're looking at. Us, we just stuff the PhD in the box. So all of this stuff I'm showing you is built into our system. I was leaning against a table and I'm listening to that conversation going, some salespeople are that slimy when their technology is not good enough to compete with another, so they have to badmouth it. So, by name. I'm not going to name their name. I don't want to give them anything. So here we go. And then through that, through Babbitt. Now, this was another thing. When we're taking data, I'm watching people put vibration transducers horizontally, and my favorite is from the top down in a Babbitt-style bearing. And you basically have a bell. We talked about this last week. There's a structure. Even underneath, there's a structure. You have a globe, and you have some structure and everything else. I'm going to talk about this in more detail later on with pictures of bearings. You know what? We'll do that maybe next week. I'm about to head out to do wind turbines, so I may do something on wind turbines next week. But I'm definitely going to cover a little bit on bearings and reading bearings, because I tell you, we're seeing an awful lot of interesting things. So in any case, we came up with this. So part of this all was when I got finished, I pulled up a little calculator. I'm going to pull up 2 copies of it here. It's not large, it's only about 21 megabyte, but I'm still using Camtasia. Don't shut me off. Okay, I'm going to pause for a sec. Okay, so here's the little calculator. I put up two versions of it. Now I'm going to do this from a vibration analyst standpoint. So we're going to do RPM, the weight of the machine, which we're starting to see this on nameplates. Primarily, it's an OSHA thing, so that you know what the weights are that you're moving and so on. We'll do it in inches per second. Okay, and let's say we just we're going to use 8760 because I want the number to be big. Or you know what? Let's do 6,000 hours. That's 5 days a week, 3 shifts a day, weekends off, 2 weeks off for Christmas, right? So we have this. We're going to use the present value of 0.699 tons of CO2 per kilowatt. So let's duplicate this one over here so that we end up doing the same. 6,000 hours. You could do a lot of other things in here, but we're going to do this from the standpoint of what happens if we reduce vibration. So we take a measurement of speed. So let's say the speed of the machine is, actually it's supposed to be, the reason it just says frequency, we're going to do a one-time RPM here, but that's for the frequency associated with the specific peak that you're interested in. The curve this is based off is off of individual defect frequencies. So let's say I'm looking at an 1800 RPM motor that's running at 1785 RPM. Let's say it is a larger machine that weighs, let's say it's let's go with a smaller motor. Let's say it's a 500 horsepower and a 440T frame that will end up weighing somewhere around 1,500 cast. So we'll just say 1,500 kilograms, and then we'll come back to this. So let's make sure these are the same, 1785, because really, it's going to be a rough estimate. So I have this. Now let's say I have drive end vertical of we're going to make it real simple. So let's say it's highly out of balance. So 0.4, 0.5, and just to keep it easy, 0.4. 0.5. Actually, we're going to do 0.6 on both, just so when I drop it by half, it stays that way. So we have a high level of unbalance. 0.2 is bad, is the borderline bad in the case of this machine. So we're going to calculate this, and there's the losses. So it's 5.25 kilowatts lost due to unbalance. That's direct energy measurable losses, right? So a portion of my load on this machine then is feeding that unbalance. That ends up being 22 metric tons of CO2 and about 3150, 3,150 USD. So let's take this now and we say, okay, what we're going to do is we are going to bring it into balance, just into 0.2 inches per second, 0.2, and 0.2. Or you know what? Let's say for this one we're going to just have it and bring it. We're going to have that on balance. And then what I'm going to do then is I'm going to start up another calculator as well. Let's see if I can do this. I'm going to start up a couple of them. Probably have to pause again, but so. And anyways, while we're waiting for it to do that, let's go ahead and calculate. So here we go. We didn't, just by having it, it's not linear. 5.25 kilowatts drops down to 1.3 kilowatts, or 1,300 watts. That more than halves the kilowatt hours, right? So I drop down from 31. So I'm out of balance here. I'm just on the edge of being in balance here. And that drops me from 22 tons to 5 tons, or almost 6 tons. So that's a 15 metric tons of CO2 a year dropped just by bringing it into balance, right? Energy cost 3,100, and that drops it down to 787. So I'm going to pause while I'm going to get 2 more of these up, because we're going to do an in, and then we're going to do a precision. Oh, wait a minute, I don't have to. Here we go. And while I'm doing this one, I'm going to start up another one. That's one of the nice things for the comparison. I want to do something else with this, but for now we're going to do this. So 1785, 1500, because there's a lot I can do with this now, right? Inches per second, 6,000 hours. Obviously, numbers are going to change based on this, or if I've got varying loads over the year, but that's not the point, right? So let's take a snapshot in time, because if I'm not changing the operation, the percentage changes are going to be roughly the same. So we come in now and we take a look at this one, and let's say we go for something a little more precise, and we're able to get the one-time RPM down to, well within. And in this case, we're going to bring this to 0.1 as well, and just do 0.1 all the way through. So, theoretically, we're at 0.1 now, and then we calculate that. So this is yet another huge leap, right? By reducing it by just over half, we now go from 1,300 watts down to 200 watts. That's 1,250 kilowatts. That brings us down to $126. And then we're also dropping now down into pounds. Now it's 2,240 pounds of CO2 per metric ton. So we dropped from 22 metric tons to just under a ton related to this particular defect. Now let's say we go all the way and we do a precision balance. And we're going to just keep everything the same, even though really what's happening is we're going to see this speed increase a little bit because the load's going to drop. And let's say we go to a 0.0, half, so 0.05. And then there's all kinds of things I can do with this at this point. I recommend, having the inches per second. If you accidentally leave that as meters per second, you're going to end up with a big number. And then 6,000. And of course, all this stuff can be adjusted accordingly. So let's calculate. Look at that. We're down to 100. Whoops. That should not be. I did something wrong here. There we go. RPM. Yeah, that was a. So if I half it, again, look at that. It's not linear. I dropped this to 1/4, basically, of this. I am at 315 kilowatts. The energy cost of that remainder is only $31, and it's only 439 pounds, or 1/4 metric ton of CO2, right? And if I dial it in even closer, let's say if I come in and I see a value even tighter than that, I know that value is going to be even closer. So if I take this machine back here that was out of balance, right? I correct what's probably a resonance, improve the stiffness and do some other stuff. That's going to take this 5.25 kilowatts, which is, by the way, basically a 7.5 horsepower loss. That's going to bring me down to 52 watts, or 0.05 kilowatts. So 100, what's that, 1/100th of that? And then I'm going to drop down. You can see, because I'm having and everything else, this is like a fraction, right? So that's, this is 1/100th or 1,000th of this, 1/100th of that, just by taking and doing a precision balance job, right? And then the cost, again, just because the way I'm having it on the curve, it's dropping by 1/100th. So I save 1/100th. Okay, I reduced the cost to 5%. I'm sorry, 1% of this original here, down to $31 versus, that unbalanced costing me $3,100. So that means once I start balancing this to improve the life of the bearings, because that's the other thing, is the bearing losses are not linear either. And I've done, I haven't done a presentation here on that yet, but I've done papers and other stuff on the impact of unbalance on the life of a bearing. So I've taken this and I have gone from unbalanced, so very poor, so the bearing life on this is going to be, let's say if my bearing life would have been 20 years, that would make this like 3 or 4 years. This brings it up to, over 10 years without any lubrication issues. So in that case, that's basically the purpose of this, was to demonstrate as I continue making improvements, I can improve my losses. Let's say, just for fun, let's take a look at a bearing signature. We'll do an outer race on a specific machine, 1,500 kilowatts. So that's going to be, say, a 6318 bearing. That would be 10 point something. So let's say 1785. divided by 60, which gives me hertz, times, let's say, 10.25. It's not that number. I'm just going to come up with something. So we're going to say that's 304 hertz. I think this is a float, so it should handle that. It's 1,500 kilogram machine. The bearing I'm looking at, we'll just say we're looking at a peak of 0.01. 0.08. Okay, so it'll be the drive end bearing. So let's go 0.009. Okay, just for fun. So the actual numbers don't mean anything. I'm just tossing in something that's reasonable. So my losses across that defect on that race, this should be probably the inner race, would be about 159 watts of loss. So that means 1,500 pounds of CO2. That's still a fair amount. So chances are, if I report out to management, that this increasing defect is costing us $96, and CO2 emissions are here, they may act on it. I usually say, whenever I get down under like 1 or 2 pounds, 1 or 2 metric tons of CO2, I convert back over to pounds of CO2. But let's say I've got a worsening condition, and we'll say 0.015, 0.011, and then we'll leave this the same over here. Calculate it, and you can see my losses are starting to go up. I can start tracking the condition of that. Now this is off a single peak. I can add the peaks together. So if I have several peaks at that, take the average frequency associated with it. Say I'm at the second harmonic. So let's say 7, that would be 304, 304 be 610. So let's say 611 hertz. Say I'm only seeing the second harmonic at that. I calculate it, then that gives me a higher number, and so on. So, as my problem gets worse, as other things go on, I can start calculating those peaks. But right now, I can only do it by a frequency. I may make something a little more complex that'll allow me to take multiple frequencies to add them together, that kind of thing. Or I can do one here, one here, one here, and add them up. That's part of the reason I made these this size. But in any case, that should give you an idea of how to look at watts and kilowatts and the impact on any type of process I'm doing. And with that, I would like to say adieu, and I'm about to head out the door to another site to test about 100 turbines, and if I have good wind, that's 3 days worth of work. So have a ball.